Hey, I'm going to make a quick video about the free response. Number one, you can adjust your settings, by the way, and slow it down if you need to, or just pause or whatever. And so here's our normal force acting on the car. Here's the force of gravity, mg. We know that the car does not accelerate in the y direction here, and so ny should equal mg as well. And that just leaves this component, which I'm going to call n sub x, as our centripetal force. And we know for anything moving in a circle, the net force is the centripetal force. And so our centripetal force is mass times centripetal acceleration, which is mv squared over r, or mass times v squared over r. And our net force here is, like I said, it's the horizontal component of the normal force. These two cancel each other out. That's all you're left with. Okay, excuse me. Also, this angle that's in here is also equal to the ramp angle, and you can do a little geometry to figure that out, but I'm not going to do that right now. But I do know that if I take the opposite side, which is nx of this angle theta, and I divide it by the adjacent side, ny, and I take that ratio, I take the inverse tangent of that ratio, that will equal my angle theta, which is what we're asked for. Well, nx is mv squared over r, and my, as we said, was mg. The m's cancel out. We can move this g right here, just to make it easier to look at. And now just substitute your values for v and for g and r and take the inverse tangent of that, whatever that number is. I'm not going to do that. I trust that you guys can operate a calculator. So number two talks about the car, and we're looking for the velocity the car should travel with a certain radius and if it's banked at a certain angle. Well, really we're back to the same spot, right? We've got the only thing causing this car to move in a circle, a horizontal circle that is, around this banked curve, is this component of the normal force. And so we get back to the point where we're looking at, excuse me, guys, that the net force, of course, is the centripetal force. That's true every single time. You should really start with, this statement every time you do a circular motion problem, that the net force is the centripetal force, and the centripetal force is mass times centripetal acceleration, which is v squared over r. And here our net force is n sub x. Well, very similar to the first problem, but this time they give us the angle theta. So the tangent of that angle theta will equal the opposite side, nx, divided by our adjacent side, which is mg. And so all we have to do here is rearrange this, multiply both sides by mg, and we've come up with the fact that nx equals mg tangent of theta. We will substitute that in here. So mg tangent of theta equals mv squared divided by r. And the m's cancel out, and we're trying to solve for v, right? So we'll multiply both sides by r, and then we'll take the square root. So we get the square root of ger tangent theta equals v. Again, I'll trust that you guys can operate a calculator to do that. Number three, just apply a little logic, right? If the car is going faster, if they exceed this velocity that we come up with here, we need more centripetal force to keep the car on the road if it's going faster. And so in addition to having your normal force this way and your force of gravity this way, you would need some friction heading down the ramp if you exceed this speed. Of course, if you're going slower than this speed, friction is actually going to have to keep you on the hill by pushing you up the hill. Number 4a, it's really the same exact problem as number 2, so I'm not going to bother going through that. Number 5, Number 5, let's just put the paper right there. Cool. Determine the magnitude and direction of the net force on the ball which at the top. Well, when it's at the top, right, the tension is pulling it down, force of tension, and gravity is also pulling it down. So we want all our answers in terms of M, L, and G. So at the very top, it also says the tension in the string is twice the weight of the ball. So the force of tension is 2 mg. And so if we're looking at the net force, and this is our free body diagram, our net force will be 2 mg, which is your tension, plus mg. And so that will equal 3 mg altogether. And now if we want to know the speed at the top, we got to start with that same statement that we said we were going to always start with, is that the net force is equal to a centripetal force. Whoops, that's supposed to be F sub c. And so we've got our net force, which is 3 mg. We just established that. And that will equal m times v squared over r. Look, the m cancels out. Woohoo! And then we'll have to multiply both sides by r. And then take the square root, of course. And so that v, I guess they're calling it v naught rather, will be the square root of 3 grr. Cool. Now, the string breaks when the ball is at its highest point. That's not likely. It's more likely to break at the bottom. But determine the time it takes the ball to reach the ground. Well, guess what, you guys? You are so lucky, because this turns into a horizontally launched projectile problem. The v-yo, the initial velocity in the y direction, is 0. The vx equals v naught that we found here. So we also know that we just cleared the ground, so the distance to the ground was 2 times L, right? It's L from here to the center and another L all the way to the ground. Cool. And that's all we need, really, because we know the acceleration in the y direction is g. Sweet. So we can just substitute into our formula the x equals x naught plus v y naught. I guess this should be y. Y equals y naught plus vy naught times t plus 1/2 acceleration in the y direction times the time squared. All right, so we'll call that 0. It follows a distance of 2L, and this is also 0. And 2L would then equal 1/2 gt squared. Multiply both sides by 2 to get rid of the 1/2. Divide both sides by g to get rid of the g over here, because we want to solve for time. So that goes away, and then take the square root. And so we get the square root, the time, equals the square root of 4L over g. Or we could say that's 2 times the square root of L divided by g. Sweet. Okay, the horizontal distance the ball travels before hitting the ground. Well, remember, horizontally, projectiles move at a constant velocity. So the horizontal displacement is going to be just the velocity in the x direction times the time. Velocity in the x direction was v naught, which is the square root of 3 grr, and the time is 2 times the square root of L over g. My. Look at this. So now we've got 2 times the square root of 3 g r L over g. Look, the g's cancel. And so we're just left with 2 times the square root of 3 RL. Sweet. Okay, we're moving on. All right, so now we've got a horizontal circle, and wow. The time required for the object to hit the ground after the string breaks. That's just like what we just did, right? Except now we've got h, right? So h would equal 1/2 gt squared. So time is equal to 2gh square root when we rearrange that for time. The horizontal distance the object travels, same thing we just did, right? So we'll just take delta x equals vx times t. Vx was v naught, right? Because this thing is a horizontal circle, it's moving at a speed of v naught. So that's our initial velocity, and we'll multiply that by the square root of 2gh. The speed of the object just before it hits the ground. Well, here's a pickle. It's going to maintain all of this initial velocity in the x direction, right? So when it hits the ground, it's not only moving horizontally, though, it's also moving vertically. So this is V naught times the square root of 2gh. It's also moving vertically. How fast is it moving vertically? Well, it's moving vertically if the time was square root of 2gh, and the initial velocity in the y direction was 0, and it was accelerating at a rate of g, we can use our first kinematics equation to figure this side out, which is Vy would equal V naught Vo, which is 0, plus acceleration times time. So that equals g times the square root of 2gh, okay? Now, I'm not going to bother, should I bother? Use Pythagorean theorem, right? I've got two sides of a triangle, right? If I just move this vector over here, they're asking for this overall velocity. So that squared plus that squared equals that squared, and yeah, why not do it, right? So I got V squared equals VO square root of 2gh squared plus, can you guys see this? Yeah. G times the square root of 2gh, and I'm squaring that. So I get what? V naught squared times 2gh plus g squared times, oh, I'm sorry, that's not 2gh, that's 2h over g. 2h over g, crap, and this is 2h over g. Okay, and that's also 2h over g, crap. Maybe I shouldn't have done this. Oh well.